Okay, so as I've mentioned the other day, this is the unit where we're going to focus on solving quadratic equations, right? We're going to take a strategic approach to this, and by the end, you're going to be really good at this. You're going to be able to determine not only how can I solve any quadratic equation, but how can I do it most easily. You're going to be able to look at this and say, okay, this one is one where I should solve by factoring. That's the quickest and easiest way to do it. Or this is one where I can't solve by factoring. I've got to move on to something else. We're going to look at another option. We're going to look at a type of quadratic equation that we can solve in a way that is different from factoring here. Factoring would be much harder to do than what we're going to look at today. So here's an example of the kind of quadratic equation that we're going to tackle today. Quadratic equations of this kind. Okay, so the question is, how could we solve that? Okay, how could we solve that? Any ideas?
You could subtract 76 from both sides and then it would be a difference of squares.
Okay, yeah, I could in that case. That's very good. I could subtract 76 from both sides and it would be a difference of squares. Okay, that's true. Very good. I could, what if that were like a 74 instead of a 76 though? Then I'd have a little bit of a problem there, wouldn't I? I wouldn't have a difference of squares. Okay, so there is a way we can do that. Say it again.
Could you move the -5?
I could move the -5 to the other side. And I'm going to take you back to something that we talked about earlier in the year. Do you remember me saying that when we were solving linear equations, that whenever you can point to a single variable, you can isolate it? Remember talking about that? We did a bunch of stuff like that when we did our review section at the beginning, right? Well, look, there is an x right there that's sitting by itself, and so I can isolate it. Now, I want to temper this. When we get into bigger polynomials, there is a little bit of a danger in trying to do that. So really, isolating a variable, although it's something you can always do, when you get beyond quadratics, you have to be very careful with that. You have to be very, very careful with that. But when you're dealing with quadratics or smaller, polynomials that are either quadratic or linear, you can always conveniently, if it's convenient, if you can point to a single variable, you can always just isolate it by reversing order of operations, right? So there is a single variable. This is quadratic, right? How do we know it's quadratic? Because if I were to expand this whole thing out, would everybody agree here? We're not going to do this, but if I multiplied the whole thing out and collected like terms, I could get this into a quadratic equation in standard form, couldn't I? Everybody agree? If I FOILed out the 3x minus 4 and I subtracted 5 and then I subtracted the 76 to the other side, when all the mathematical dust settled, I would end up with a quadratic equation in standard form. We can all see that that's a possibility, right? Okay, so it is quadratic and I can point to a single x, and so I should be able to then just reverse order of operations here. And solve for x, okay? All right, so then what does that amount to? I can point to a single x. So first, in my quest to isolate the x, the first thing I have to do is add or subtract, right? Well, is there something to get that x by itself? Adelaide, what's my first step? What do I need to add or subtract to help isolate that x? And you already hit the nail on the head. What do we do?
Add 5 to both sides.
There we go. We add 5 to both sides. So there's my first step. And I get the quantity 3x minus 4 squared equals 81. Okay, next step. Is there anything for me to multiply or divide here? Do I have to undo any multiplication or division to get that x by itself? Keeping in mind that I don't get to undo parentheses until the last step. So this would all be things that are outside of the parentheses. Nothing there, right? I don't need to multiply or divide anything outside of the parentheses. So I could just cancel, I could skip that step. What about exponents? Yeah, there is an exponent, isn't there? Right? That I have to undo. How do I undo a square root? Yeah, by square rooting, right? Everybody see that? Okay, so that's where we're going to leave our path, because I bet you we need a little practice with that, right? I bet you we need a little practice with dealing with radicals. We haven't done that at all this year. You probably did it a little bit in Algebra 1, but we'll come back. We'll come back to this problem and we'll finish it later. But for now, let's do some focusing on just the radical part, because if we're going to be square rooting both sides, we're going to be taking square roots of numbers. Those numbers might be fractions. We got to know how to deal with all that stuff. Okay? So we're going to just do some back to basics practice here. First thing doesn't even seem like it's connected, but it is. I want you guys to help me write this number in prime factored form. So here's our number. I'm going to write it over here so it's centered a little better. How would you go about factoring that big number? Remember doing this? I'm sure you must have done this in Algebra 1.
Would you just square root it, like to find the square of it?
Okay, well, we're not going to deal. We're not doing square roots yet. This is just kind of a prerequisite, just a little bit of back to basics practice to get us ready for simplifying square roots. But for now, all I want you to do is just factor this. What does it mean to write it in factored form, in prime factored form? Like, let's take an easier one for a second. Let's take something like, how about 12? If I want to write 12 in its prime factored form, what would it be? What are prime factors? Factors are things that are multiplied, right? So the factors of a number are just the numbers we multiply to create that number, right? To create that product. Prime means they're prime numbers, right? Numbers that are only divisible by themselves in 1. So what are the prime factors of 12?
3, 2, and 2.
Yeah, 3, 2, and 2. Everybody agree? So that's, I could write this as 2 times 2 times 3. And I can't break it down any further than that, can I? Right? 2 is prime and 3 is prime. So I could just write that as 2 squared times 3. Okay? Prime numbers are, 2, 3, 5, 7, 11, 13, etc., right? Numbers only divisible by themselves in 1. Okay, that one was pretty easy because it was a small number, but how are we going to organize this factoring? How would you have done this, back in the day when you were doing a lot of factoring? How would you have broken this down to its prime factors? There's kind of a way to organize the factoring.
For this one, you could do like you divide it by 2, and then you continue dividing like.
Okay, exactly. Perfect, yeah. So we could factor out a 2, right? How do we keep track of them all? Do you guys remember a factoring tree? Have you ever worked with factoring trees? Okay, that's a good way to do this. So if we split this thing up, every time I factor out a number, I'm going to split the tree, right? So it's even, so I know 2 divides into it. 2 goes into 25, 20, what? 12, 60? Okay. Now the 2's done, right? It's prime. But the 1260 is not. How could I break that up?
2 and 630.
Okay, I could take another 2 out. 2 and 630. The 2's done, the 630's not. How about that one?
2 and 315.
Okay, 2 and 315. Good. Now what?
Now probably go by 3 and then do 3 and 105.
Okay, good. How'd you know that 3 divided into 315?
Because 300, you could divide it in 300 and then also go 15, like you could do them separately.
Okay, that's true. 3 goes into 300 and it goes into 15. That's good. There's another little trick. Do you guys know, I can't remember if I've showed you this or not, but if you add the digits up of a multi-digit number, like 3 plus 1 plus 5 is 9. If the result is divisible by 3, then the original number is divisible by 3. You guys all know that trick? Okay, that's a good trick. So we know 3 goes into this. And it goes in 105. Okay, now what? That's also 1 plus 5 is 6, right? So I know 3 goes into that.
It would be 3 and 35.
3 and 35. And finally, 35. That's just, that one's going to break up into 2 prime factors, isn't it? 5 and 7. So there it is, right? So the answer is 2 times 2 times 2 times 2 times 3 times 3 times 5 times 7. Okay, so we would write that as, 2 times 2 times 2 is just 2 cubed times 3 squared times 5 times 7. There, it's factored. Okay, that ring a bell? You've done that stuff before, I'm sure, right? Okay. Okay, that's useful to us. That's useful to us because when we're trying to simplify a radical, our goal when we simplify a square root, when I say radical, I mean square root for today. We're not doing any other radicals, right? We're not doing cube roots or any higher roots. We're just doing square roots. So when I simplify a square root, my goal is to be able to write my answer in 2 parts, right? I want to have, there's going to be an outside part and an inside part. My goal is to get as much outside of the radical as possible, right? I may be stuck with some stuff inside the radical, but my goal is to get as much outside the radical as possible. Let's take a really simple example. Like, what if I wanted you to simplify the square root of 18? Can you tell me what that is? Okay, I'm going to remind you about a property of radicals. I think maybe we've looked at this once before, but it wasn't really in context. So this is a property of radicals, and this goes both ways. So if I have the square root of A times the square root of B, that's equal to the square root of A times B. Now I can go either way with that, obviously, right? That's an equation. So I could write the square root of 18 as the square root of 9 times the square root of 2, because 18 equals 9 times 2, right? Well, why would I do that? Because 9's a perfect square. What's the square root of 9 equal to? Well, you guys all know that, right? That's 3 radical 2, right? So that's my simplified version of the square root of 18. I was able to get quite a bit of the radicand, of the number inside the radical. A lot of that I was able to push outside of the radical, so I get a much smaller number stuck inside the radical. That's always my goal, right? To write it in simplified form means I have to get as much out of the radical as possible, okay? Well, another way we could have thought about this would have been to say, okay, let's take 18 and let's break it up into its prime factors. Okay, well, I could take out a 2 times 9, and 9 breaks up into a 3 times 3. Well, look, a 3 times a 3 is the same thing as a 3 squared, right? The square root of 3 squared is just 3, isn't it? In general, if I take the square root of anything, call it a squared, the answer is just a, right? Everybody agree? Okay. So my goal here then is when I factor this number, if I'm trying to get as much out of the radical as possible, well, I know that the way that happens is by breaking it up into perfect squares and numbers that are not perfect squares, right? Whatever the number under the radical is, I want to break that up into products of perfect squares and then other numbers that are going to end up getting stuck inside, right? 9 is a perfect square because it's 3 squared. So when I do my factor tree, I can notice that anytime I ever end up with a couple, I'm going to call it a couple, and a couple just means I get the same factor appearing twice. Then I know that that corresponds to a square, doesn't it? Right? And so the square root of that couple, the square root of 3 times 3, or the square root of 3 squared, is going to give me a 3 outside the radical, right? If I ever end up getting singles don't culminate in a perfect square, and so they end up getting stuck inside. So the 2 goes inside, and the 3 ends up going outside. And so there's a little saying that summarizes this. Couples go out, singles stay in, right? That's our little mnemonic device. That helps us remember how this process works. So we're going to do a prime factor tree, and all the couples end up being factors outside of the radical, and the singles get stuck inside. Have you guys ever seen this before? Couples go out, singles stay in. Okay, so you've seen this stuff before. Okay, good. All right, so then this will go quicker. So let's do this with 4410. Okay, I want you guys take this, just work on this on your own for a second, and then we'll come back together and we'll talk about it. Okay, how do we do? Let's check this out. Now, this is for an honors class. I'm going to maybe go one step further than I normally would go with a class on this. I want to talk not just about how we can crank through this, but how we can be a little more sophisticated and smart about this too. This is kind of a part, you know, we focus on algebra a lot, right? And we know, of course, everybody knows that when you work your way up in math, you start with really basic stuff, just arithmetic stuff, and then you move on to algebra, and that arithmetic stuff is not important anymore, right? Just those are just plain numbers. Now we're into variables. Those numbers don't matter very much, right? Well, it turns out there's number theory. There's a lot more to it than you might expect. We don't have to have variables involved in math for it to be interesting and complex. There's some things you can do just with looking at just static numbers that are pretty interesting. Okay, so how could we do this? How could we break this apart? Suggestions? Okay, that's a good idea. Now, it's kind of nice if we can chunk this a little bit. Instead of just taking out, you notice on that last example we did, when we just took out twos, we got stuck with pretty big numbers in there, didn't we? Right? The bigger the number, the harder it is to deal with, essentially, right? So it's kind of nice if we can chunk this a little bit and take out maybe slightly bigger numbers, okay? So we could take out a 10. Okay, if we take out a 10, and we know that because it ends in a 0. Well, 4410 equals 10 times what?
441.
441, right? I'm just getting rid of that 0 when I divide by 10. Okay, and then 10 we know breaks up into 2 and 5, right? Okay. So now what about the 441?
Yeah, I did 3 and 147.
Okay. Okay, 3 and 147. That works, right? Because 4 plus 1 is 9, divisible by 3. Okay, now what?
I took out another 3 and then got 3 and 49, and then just did 7 and 7 for the 49.
Okay. Okay, that was pretty good. There's some things we can do with this, though. It's really nice. Like when you see a 49 there, you're pretty excited. How come? Because it's a perfect square, right? So you know you're getting a couple right out of that perfect square, right? So it's always kind of nice if we can get perfect square factors in there. Okay, so that was pretty good. I'm going to just give you an alternate way of maybe looking at this. Let's take the very same problem, but let's split it up again. I'll come down here. There are some rules you can always get that you can use to factor these in addition to the one I showed you. Okay, so in addition to the rule of 3, where if you add the digits up and it's divisible by 3, then you know it's divisible by 3. Well, you can do the same thing with 9, right? Think about why that is. We were able to use the 3 twice, weren't we? We divided 3 out of 441 and 3 out of 147. Okay, well, if I'm able to add these digits up and get 3, and add these digits up and they're divisible by 3, then I must have been able to add, whoops, I'm pointing with my finger. I was able to add these digits up and get a number divisible by 3, and add these digits up and get a number divisible by 3. Then that means that I must have been able to add these digits up and have it be divisible by 3 twice, which is 9, right? So there's also a rule of 9. If I add the digits up and they're divisible by 9, then that means that 9 divides evenly into that number, so it's a factor, right? So we know right at the very beginning here, 4 plus 4 plus 1 plus 0 is 9, which is divisible by 9. So I know I can divide a 9 out, and I could combine this. I know 9 goes into this, and it's got a 0 at the end, so I also know 0 goes into it. You see my point here? And do you really have to be so precise about this? No, but it's when you deal with really big numbers, it's not a bad idea. So I know I could take, and if I don't want to take a whole 90 out, because that's kind of hard to divide, we could have just done the 10, because that's so easy to do. But then let's split this into 9 and whatever else we get, right? So 9, let's divide 9 into 441. 9 goes into 44 how many times evenly? Nine goes into 44, because we can do this long division just kind of tabularly here, right, in our head. 9 goes into 44 3 times, right? Or sorry, 4 times, not 3 times. 4 times 9 is 36, right? So how much is left over then? Well, there's an 8 left over, isn't there? Right? I'm not worrying about that 1. I'm just focusing on the moving from left to right. 9 doesn't divide into 4, so I move over now. Doesn't divide into 4, but it does divide into 44 4 times. 9 times 4 is 36. So there's 8 remaining. So then I'll just look, how many times does 9 go into 81? 9 times, right? And then look what I get. Now I know that I've got a couple of 3s and a couple of 7s, right? And at that point, I don't even have to go up here and break this thing down, right? Because I know the factors I'm getting out of this are going to be a 2 and a 5, and they're not going to, neither the 2 nor the 5 will couple with any other numbers here, right? I've already got couples. All the other numbers are already, they're already within couples, right? And so I don't even have to break that 10 down into a 2 and a 5, right? And I get the answer then. Either way, I know I'm going to, whether I do it the blue way or the black way, I'm going to get the same answer, aren't I? If I did it the black way up here, let's look at this result real quick. So let's go ahead and make a convention here. Let's go ahead and put, and you can do this on your own however you want to, but let's go ahead and put circles around couples and boxes around singles, right? So look, there I've got a couple of 3s. Here I've got a couple of 7s. And I've got some singles, right? So that means I'm going to have a 3 outside because I have a couple of 3s. I've got a 7 outside because I have a couple of 7s. And let's color code this and maybe like make these orange. How about? And then inside, I've got a 2 and a 5, right? Down here, we just would have said, okay, we've got a couple of 3s, couple of 7s. And then inside, I've got a 10 that I know is going to produce no couple, so I just leave it as a 10. So my final answer either way just looks like, whoops, not 27, 21 times the square root of 10 is my simplified version of that. Does that make sense? Okay, there's some other rules. I won't go into like ridiculous. Some of these are a little bit arcane, but there's some other rules. Let me make up another problem here real quick. So how about, let's see. Okay, what if I wanted, let's do one more of these. What if I wanted to do this? Okay, so I've got to factorize 1, 2, 3, 2. What could I do? Not divisible by 3, is it? It's even, so I could break it down in 2s, right? Agreed? Okay, here's another trick. Is it divisible by 4? It is, isn't it? Anybody know? How can you tell?
4 goes into 12 and 32.
Okay, goes into 12 and 32. Even if this were something like let's say it was something like 1732, it's still divisible by 4. How do I know?
Because it goes into 32.
Because that's it, because it goes into 32. You know that anytime 4 is going to go into any number of hundreds, isn't it? Agreed? Because 4 goes into 100 evenly, right? So the moral of the story here, this is a pretty cool rule. So if you want to know if a number is divisible by 4, all you have to do is look at the last 2 digits. If the final 2 digits are divisible by 4, then the whole number is, right? Because beyond that, you're talking in numbers of hundreds, which of course it's going to be divisible by 4. That's pretty cool, right? So you know this is divisible by 4 right away, right? So 4 goes into 12 3 times, and it goes into 32 8 times. Okay. I can do it again, right? Because 8 is divisible by 4. Everybody see that? So I don't have to mess with those little 2s, right? I can jump right to 4s. Okay. So I end up with 4 times, and then 4 goes into 30. What is that? 7 times with 2 left over. And then it's 77, and then 77. Well, I know that's just 7 and 11, right? So look what I end up getting here. I end up getting a couple of 4s and a single 7 and a single 11, right? So I know this is going to simplify to 4 times the square root, because I got a couple of 4s, times the square root of 77. Now, if I had done this, I don't want to spend too much time, but I think this is these kind of things, you guys will find this interesting. If I had broken this up by 2s, look how much harder it would have been. I mean, not like that much harder, but I would have ended up with 6, 16. Okay, you say I can do a 2 in that one also. So 2 times, 308. Can break another 2 off and make that 154, and break another 2 off and make that 77. Well, I mean, then look, now I've got to have 2 couples of 2 instead of 1 couple of 4s. It's better to just do 1 couple of 4, isn't it? It's always easier if you can get bigger perfect squares, so you don't have to have so many little couple relationships there. See my point? Probably enough said on that stuff, but you get the idea. I mean, you just want to be kind of smart about it. Try to chunk it into perfect squares, big perfect squares whenever you can when you're factoring. Okay, what about one like this? What if you have a product of radicals? Okay, well, think about this as already partway down the factoring tree, right? This is equal to the square root of some big number, 2 times 10 times 15, right? So the square root of 300, if I wanted to write it that way, if I want to work backwards, right? So if I were to take a 300 up here, well, all this is telling me is I could take that 300 and I could factor this using 3. I could break my tree into 3 branches and get a 2, a 10, and a 15. So why go backwards? I'll just start from there. Everybody see that? I can just factor from there. The 2 is already prime. The 10 breaks up into a 2 and a 5. And the 15 breaks up into a 5 and a 3. So look what I get. I get a couple of 2s, a couple of 5s, and a single 3. Right? So I get, outside I get 2 times 5. Inside, I get a 3. Okay, see my point? So like you can see, it's not that big a deal when I only have 3 of these things, but what if I had a product of a whole string of radicals? A lot of the work's already done. It's already been broken up into a product of 3 factors for you, right? Just go from there. Okay? How we doing? Give me 1 to 5, everybody. Okay? Okay. Okay, so now let's work on simplifying some radicals that involve quotients. Okay? What should I do here? I got some options. We have the option, if there's a property of radicals, and I'm sure you guys know this, but the square root of a divided by b is the square root of a divided by the square root of b. So I could just split this up into the square root of 36 over the square root of 16, right? And be done with it. Well, I'm not quite done with it. Square root of 36 over the square root of 16 gives me 6 over 4, which I could reduce to 3 over 2, right? Is there another way I could approach this?
Can you simplify this fraction?
Yeah. There are implied parentheses around, well, how do I say it? The radical groups whatever's inside, doesn't it? Right? If we technically follow order of operations, we always want to simplify inside before we do anything else, right? Before we split this up. So why not simplify the radicand? Whatever's inside is a fraction that does reduce. 36 over 16 reduces to 9/4. And that's just going to get us to that answer more quickly, isn't it? Right? In this case, it didn't really make much of a difference, but it could. If you had really big numbers there to deal with that maybe weren't perfect squares, can you see that you definitely want to make that fraction as small as possible before you start to do any simplifying? So always reduce the fraction first if you can. Okay? All right, what about one like this? Do you remember what you have to do with this? If I want to write this in simplified form, I can't, there's the square root of 7 there are no couples there. So am I done? I mean, I could be done, except for the fact that mathematicians are famously, they're just kind of finicky about this stuff. And they don't like to have radicals in the denominator. They like the denominators to always be rational numbers. They don't like denominators to be irrational. And so we've got to do something called rationalizing the denominator here. Okay? We need to rewrite this in a form where the denominator is a rational number. The numerator can be irrational, but the denominator can't. Right? And so you might have maybe heard the little statement, no tents in the basement, right? No radicals in the denominator. Okay, so we got to get rid of that. So how do we do that? How do we rationalize the denominator here? And I want you to think about this. Think about this in terms of some of our properties, right? What can we do here to this thing? Well, we don't want to change the value. If I plug this in a calculator, I'm going to get some decimal answer, right? That decimal answer can't change. It's got to stay the same regardless of what I do to this. The value of that quotient must not change. There's only 2 things I can do using my properties of real numbers to preserve the identity, preserve the value, in other words, of that number. I could add what and have it stay the same, have its identity stay the same. What number could I add to something and not change its value? 0. Yeah, that's the additive identity, right? Our identity number for addition is 0. Or I could multiply by 1. Yeah, and that's almost always what we do in math. We multiply by 1 in a fancy way. 1 is the multiplicative identity, or the identity number for multiplication. So we've got to multiply by 1. Well, would you agree that any fraction that has the same numerator as denominator is equal to 1, right? Okay, so we know we have to multiply by 1. I have to have the same thing on the top and the bottom of my fraction, but the denominator is really what determines what that needs to be. What do I need to multiply by on the bottom to get rid of that radical? How can I multiply the square root of 7 by something and get a result that is not a radical, that is rational?
Don't you like multiply it by itself?
There you go. I multiply the square root of 7 times the square root of 7, but I need to have that on the top too then, right? So this whole thing is just equal to 1, right? And then I multiply fractions straight across. And I know you guys know this. So the square root of 7 times the square root of 7 is 7. On the top, I get 6 times the square root of 7. And there's nothing I can do to simplify that any further, right? 6 over 7 does not reduce, and 7 is prime. So that's my answer. Okay, is that ringing a bell? Remember doing this stuff? Okay, a little bit? Okay, what about one like that? Can I reduce 5/12? No, I can't. Can't reduce 5/12. And so I'm stuck with, and I'm going to split this up into separate radicals. So after I've reduced the fraction, I split the radical. First step. Okay, now what do you think? What's your intuition tell you here? What am I going to do? Any suggestions?
We'll probably do the thing that we just did where we times it by the denominator.
Okay, so we could rationalize that by multiplying through by the square root of 12 over the square root of 12, right? And on the bottom, I'm going to get a 12. On the top, I'm going to get the square root of 5 times the square root of 12 is the square root of 60, right? Okay, now I've got to break that apart. I've got to simplify the top. Well, I know 5 and 12 are factors, right? 'Cause that's what I multiplied to get 60. So some of my work is done. What about the 12? What's that break down into? We'll do 3 and 4, right? Because then I get a perfect square out of it. 4 divides into 12. So I get a couple of 2s and a single 5 and a single 3, right? So I'm getting 2 times the square root of 15 divided by 12. Am I done? What else? I've got 2 times 15 over 12.
Can you simplify it?
I can. What do you mean by that? What else can I do to simplify it?
2 12ths is the same as like 1/6.
There you go. Right. I could think of the 12 as being a 2 times 6 and cancel the 2's, couldn't I? I can cancel like factors top and bottom. Everybody agree? Because the 12 breaks up into 2 times 6, I can write this as the square root of 15 over 6. And now I'm done, right? Okay, that worked all right. But we could have done better. What could we have done differently? I do this a lot, don't I? We do something and then we're going to go back and see if we could do it better. Let's go back to this step right here. What could I have done to make this easier?
Can you simplify the radicals?
Yeah. Before we rationalize the denominator, we always want to make the square root as small as possible in the denominator, right? So we could simplify that 12 into 2 radical 3, couldn't we? Everybody agree? Square root of 4 times square root of 3. Well, look how much easier that is now. I can just multiply top and bottom by the square root of 3, and then look what I get. 2 times the square root of 3 times the square root of 3 is 3. So on the bottom, I'm getting 6. On the top, I'm getting square root of 5 times square root of 3. Well, that's square root of 15. And there's no couples there, right? Because 15 factors into 5 and 3, which are both prime. Easier, right? You see the moral of the story? You want to always simplify the radical in the denominator and the numerator too while you're at it. You might as well, right? Simplify both radicals, top and bottom, before you go any further. You split the radicals and then you simplify the radicals, and then you rationalize if necessary. Okay? Okay, what about one like that? Simplify the expression.
We're out of time, but can we do, like, simplify the fraction, 7/14?
Yeah. So I know we got to go here, but we could, this is a common denominator, right? So we can always split that into 2 separate fractions with the same denominator. So we would just write this as 7/14 minus the square root of 98 over 14ths. And then that's just a 1/2. And this is whatever we get when we simplify the top, right? Does that make sense? So the moral of the story there is just break it up into 2 fractions so you only have a radical in one of the 2 fractions in this case. Okay, everybody good? All right, that'll get you going on the first assignment. Next time we meet, we'll start talking about how we can apply this actually solving some equations, okay? All right, have a great day. I will see you on Friday.